All right. Hi, everyone. Welcome to the Global Heatful Day 2026. My name is Belay, and I'm PhD student at the University of Melbourne, Australia, at the School of Geography, Earth and Atmospheric Sciences. And I'm closely working with Dr. Graham Bismore, who is a senior research fellow at the University of Melbourne. So during my PhD project, I'm working on temperature modeling, heat flow modeling, thermal energy estimations stored in the geothermal reservoir. So the title of today's talk will be heat flow modeling in one of Australian onshore Gippsland basin, which is named as or onshore Gippsland basin. So the scope of today's talk will be building 3D geological model of the onshore Gippsland basin. In this section, we are going to see how we are going to build an appropriate 3D model, which is showing the internal architecture of the basin, conducting 3D numerical temperature and heat flow modeling. And finally, we are going to see constraining the model with surface and the borehole temperature data. So here is the overview of the onshore Gippsland basin. So in this slide, we are going to take a look where Gippsland Basin is located, what's the geological time range, and the sections of the basin itself, and what are the geological resources in the onshore Gippsland Basin. So if you take a look at this map, this is the map of Australia, and the Gippsland Basin is usually located in southeastern Australia, which is sitting on the top of highly deformed basement rocks. So you can take a look. This is the Gippsland region, which is shaded in green, and this is the small rectangular colored as orange shows the steady area. And the basin has very long and dynamic history, and its origin or formations goes back to the breakup of Gondwanaland during late Jurassic. So the geological time range, of course, goes to late Jurassic to late Cretaceous through the Cenozoic era. And there are, of course, two sections of the basin itself. So we have the onshore parts where we can see this is the coastline. And if you go toward the west, we have the onshore, and all the way here is the offshore sections. So the onshore section comprises only 25% of the basin. And this entire Gippsland Basin is home for Australian oil and gas. We have coal deposit as well, and heat associated with the groundwater. So in terms of exploration, Gippsland Basin is extensively explored for fossil fuels such as oil, natural gas, and coal. But when we come to the exploration of geothermal energy sources, it is under explored and underutilized as well. So we can take a look some petrohydrogeological properties of the source rock that's responsible for storing both the heat and the water. So here it has high permeability and the porosity, and you can see the figure porosity goes up to 43% in the basin. And it has also a high specific yield capacity with estimated production potential of approximately 70 to 100 liters per second, or sometimes goes up to 150 liters per second, which is pretty high compared to any sedimentary source rocks in different parts of the world. So here is the geological setting and stratigraphy of the onshore Gippsland Basin. Is the left side map shows the major geological structures and some basement outcrops in the basin. So as I mentioned earlier, there are two sections of the basin. So this line is the coastline that's separating the, it is the boundary between the onshore and the offshore. So all the way to the east is the offshore, and this part is only the onshore comprise just 25%. And the rectangular greenish shape is the extent of the study area we are currently conducting the research work. So the basin is also very prone for different geological structures. So we have two sets of major geological structures bounding by the north and by the south. So here we have two major structures by the north, Lake Wellington faults and Rosedale faults, which are nearly running parallel to each other. And by the south, we have the Darimian faults and Fossa faults as well. So they can easily determine the thermal structure of the basin itself. And we have some also anticlines and monocline structures, which are developed during the Oligocene compressions. And the right side figure shows the major stratigraphic units in the basin. So here we have the three major stratigraphic units aged as a Cenozoic. So the topmost one is the Haunted Hills formations. So the name of this stratigraphic unit usually comes from the Australian stratigraphic unit database. And that's sitting on the top of the Latrobe Valley subgroup, which is the coal-bearing units within the basin. So this is responsible for trapping the heat and groundwater. So any heat source that's coming from interior subsurface of the earth or diverted back to the reservoir. And this geothermal source rock is what we are much more interested. And it's underlain by the Mesozoic sediments, which is also known as Silicic group, which is slightly muddy and some shelly compositions that's sitting on top of the Paleozoic basement rock, composed of granites and the metaclastic sediments or volcanoclastic sediments. So to conduct especially temperature or heat flow modeling, we have to first build an appropriate 3D model, which is depicting or showing the subsurface structure of the Earth. So when building 3D model, there are several methodologies we try to follow. First one is data collection and preparations. Of course, we have several intensive boreholes drilled for petroleum explorations, coal explorations, and groundwater as well. So we can we collect these borehole data, and also we have the topography as well, showing the superficial features of the Earth. That's coupled with the geophysical data such as seismic and gravity data. So we can easily constrain the 3D model. And once we collect and prepare all these informations, we can import this into Leapfrog Energy software, which is handy in developing a 3D geological model. So this is the central figure that shows the 3D model, which is built from these data sets and showing the major stratigraphic units I have shown you here. And we translate this the previous 2D into 3D geological model. So you can see here at the topmost, we have Haunted Hills formations, which is most likely composed of the unconsolidated sediments and some sand particles. And that's underlain by the coal, which is thermal blanket. And sitting on top of geothermal source rock. And the basin is actually bound by the South Silicic Range, and it is bound by the Paleozoic basement, which is composed of granitic rocks in the north. So once the 3D geological model is built, we can export the model, and then we can conduct into 3D numerical temperature or heat flow modeling. So after building a 3D model, we export it, and then numerical model is done in underwater software, which is a geodynamic software, very handy for numerical simulations. So similarly, we have followed several steps to build numerical temperature modeling. So the first, of course, step is creating an appropriate mesh by the domain of geological model built in leapfrog. Once the appropriate mesh is created, we can deform the mesh into the topography that is showing, topographic elevations into the mesh. And after that, we can assign the stratigraphic units actually built in leapfrog, and then we can assign the stratigraphs into the mesh. So you can see here, this is the clear assign stratigraphic units from top to bottom or from bottom to top. The other one is, thermal conductivity of rock units is very important, especially if you are dealing with the temperature or heat flow modeling. So we usually use previously existing thermal conductivity values from the already done in 2015, let's say back in 10 years. So those measurements were done by using divide bar. You can see here the divide bar picture usually taken from work of my supervisor. And we slightly paid attention on the thermal conductivity of the coal unit in the basin. This is because when we take the composition of the coal, it has no uniform like a single coal. So it comprises intercalations of different lithological units such as sand, silt, clay, and other gravels. So by using lithological logs, we can easily identify the proportions of each lithologies within the coal units. And once we determine the proportions, we can calculate the mean harmonic thermal conductivity of the entire coal units. So by using this Bridge-Moore protocol, we can calculate the inverse of harmonic mean, which is summations of a proportion of lithological units divided by the thermal conductivity of each lithological units. So by using this, we can assign the laterally varying thermal conductivity for the coal units, because just if we assign a single value, it will definitely affect the temperature and the heat flow value. So you can see wherever we have very high coal deposits, the proportions of the coal is high and thermal conductivity is low. And if you go toward the east or toward the north and south, the coal proportion gets lower and thermal conductivity becomes high and high. So this is the map of the mean thermal conductivity of the coal bearing unit we calculated. So once the thermal conductivity of rock units is collected or measured, we can assign now the thermal values for each stratigraphic units. As I mentioned, we have 5 different stratigraphic units in the basin. So each unit has its own thermal conductivity values. So we assign for rest of the units single or uniform thermal values. For example, these like basement rocks have thermal conductivity value of 3.5, and we have laterally varying thermal conductivity values for coal units, which ranges from 0.56 to 1.21. And the other thermal values of the rock unit is the heat generations, of course, generated from the due to decay of radioactive elements such as uranium, potassium, and thorium. So we can easily calculate the volumetric heat generation from each stratigraphic units by using this formula that's from these references. So gamma ray log, of course, used to calculate the heat generations, and you can see here the top units, which is composed of more sandy unit, so has a very low heat generations, less than 5 times 10 to the power of minus 7 watt-meter cubed. And if you take a look here, Suzuki range composite, which is Mesozoic in age, has a heat generation or volumetric heat generations higher than 3 times 10 to the power of 6 meter cubed. So of course, the equations used by the underworld, which it uses Poisson system solver, we have here divergent operator, scalar product, and we have thermal conductivity values here, and of the rock unit itself, that's multiplied by the geothermal gradient. So here plus AX is the heat generation from each stratigraphic units itself. So we solve for temperatures which is unknown field. And of course, we are also using boundary conditions. We have the top boundary conditions, which is coming from the ground surface temperature from the satellite data. And we have also the bottom boundary conditions coming from the borehole data. You can take a look. Most of the boreholes are not penetrating deeper into the subsurface. So the base of my model is about 5 kilometers. So most of the boreholes, the depth is less than almost 1 kilometer. So we use one D heat flow to determine temperature at the base of 5 kilometers. And we are assuming that there's no lateral heat flow in the basin. So this is the temperature profile of the study area. So it is the center shows the temperature volume. So we have the depth is going up to 5 kilometers, and temperature, of course, ranges from cold from surface to 250 degrees Celsius at the bottom of the model. And this is looking especially visualizations of temperature from different directions. For example, you are looking from the west here, temperature is slightly different, even the depth is the same. So it's again here, if you're looking from the east, you get slightly temperature is increasing in this direction. So this is entirely depends on the geology of the certain sedimentary environments. And so this is looking from the top. Of course, this is representations of the ground surface temperature. And this is looking from the north. We get elevated temperatures where we have cold deposit is thick or high. And it's also similar looking from the south, and the visualization is usually done in ParaView software, which is very good in visualizing in 2D or 3D models. So what I want to show you here is the influence of geology on the subsurface temperature distributions here. This is the geological cross-section done in leapfrog, and you can see here, here is the valley or lateral valley depressions where coal deposit is high, and we get elevated temperatures. You can see temperature gets higher and higher. And if you go toward the west or toward the east, you get is absent or very little proportion of the coal, and the subsurface heat can easily flow through these basement or highly conductive basement rocks, and temperature becomes very low. So this map shows again the top surface temperature of the geothermal source rock, or they call geothermal reservoir source rock. So you can see here the anomalous temperature and very high, not very high, but high temperature, of course, compared to the other regions. So here is where we have very thick coal deposits. The coal is confined to the valley areas. So wherever we have thick coal deposits, temperature is high. And if you go toward the north or south, the coal units are absent. So the surface become cooler and cooler, though they have the same. The temperature range of this, the top surface of the Cenozoic geothermal source rock ranges from 14 to 65 degrees Celsius, with depth approximately 500 to 600 meters. So this map, this figure shows the the comparison between the model and the observed temperatures, and we have the orange dot also showing the surface temperature, and there are some of the sites we try to compare these the depth temperature profile. So you can see there is a slightly good agreement between the observed and the measured temperatures, and there are some here, for example, there is some discrepancies between the measured and the model temperatures. So this the blue line shows the model temperature, and this the black line shows the observed temperatures. Of course, if you take a look against stratigraphy, you know, is the blue line usually straight. It's not clearly changing with the any stratigraphic boundaries, but this is because we have assigned the fixed boundary conditions at the top and the bottom. So this enforces the model temperature have like linear geothermal gradients. And here, this is the heat flow refraction of the study area. So heat flow, of course, we know that heat flow is the product of the thermal conductivity of the rock unit that's multiplied by geothermal gradients of the certain intervals. So here the negative sign shows heat usually comes from the from the hotter regions to the colder parts, especially from the mantle, from the core to the colder crust of the earth. And this here, for example, we have very wide range of heat flow, goes from 62 to 100, approximately 150 milliwatt per meter square, which is higher than average continental heat flow. And if you take a look, this especially in granitic rocks where the basement rock is exposed, we have very high heat flow. In areas where we have coal units and other sedimentary units with low thermal conductivity values, the heat flow is very is low compared to the northern parts of the study area. And if this is the same approximate extent of the study area, and you can see here from the previous heat flow map of the onshore Gippsland Basin done by Green Earth Energy in 2007. And they have produced this map at very low to 100.6 milliwatt per meter square, which is more or less within range of these also model temperature heat flow values. So areas, for example, here we have Yalon region, which is we have some faults here called Yalon fault. We get very elevated heat flow values. And we have also some point heat flow data observed by the Geological Survey of Victoria. So conclusions and takeaways, the onshore Gippsland Basin stores significant thermal energy with especially Cenozoic units representing the most promising geothermal source rock. Thermal conductivity contrasts particularly the Cenozoic coal units strongly influence heat flow refraction and subsurface temperature distributions. And of course, the 3D steady state conductive model reproduce borehole temperature data and surface heat flow patterns, supporting the robustness of the geological and thermal property framework. And my future work will estimate the volumetric heat in place and investigate low enthalpy geothermal potential within the geothermal source rock. So thank you for listening. This brings us to the end of today's presentation with me. If you have any questions or any comments, you are most welcome.